We're here with Jonathan Lizarazo, who's from the University of the Andes in Bogota, Colombia, and also working at Texas A&M currently. And he's presenting a paper on for research on transportation networks for hazardous materials and how to avoid unnecessary risks. So, Jonathan, if you could please tell us about your work and what you've been doing and what you found.
What I try to do is just like focus in minimizing risk. What we try to do is minimize the risk that is involved when you are transporting hazardous material such as diesel and biodiesel. In Bogota, my country, in Colombia, we don't have a really transportation network really developed. So what we try to do is to fix it at all. Try to minimize and try to see how many routes can be used to get the transportation really well done. So what we try to do is to use this genetic algorithm that just try to use an stochastic search to find all kind of combinations, mixing all the nodes that we use at the network to find better solutions. These are not going to find the optimal solution, but hopefully we'll find the best solution that if you just try to send all tracks between the routes. So what we try to do is to find a new methodology to measure the risk. So we found some probabilities. If you have an accident in Colombia, you will find that one of them will finish at the explosion, another one will finish at the pool, but this kind of probability. What we try to see is like to study a database specified in this kind of accidents. Finally, we put it all together at the genetic algorithm, and we finally found some different kind of routes that actually minimize risk and the distance at the same time. So we have like both goals involved in the genetic algorithm, and they try to find the best route.
Okay, so how does that work if you have a train full of a flammable liquid? You don't want it to go through a residential neighborhood, but how do you determine how many miles out of the way would be acceptable for extra fuel costs and energy, etc., to avoid that risk? How do you balance those two out?
Okay, first of all, you have to define your network. So you just use the stations, the gas stations, and the intermediate nodes. So they are going to use just like main routes, like the highways, freeways, but not at the neighborhoods, because the government does not allow you to do that.
Okay.
You cannot go inside the neighborhoods because they will not allow you to do that. So what we try to do is like to find the lowest risk, but inside the route. The people that cannot be affected by an accident. If an accident is occurring, how many people is going to be affected? We measure that, and we try to see which is the route that has the less risk. So that lowest the risk, that has the lowest risk.
And so the genetic component here is you're crossing a risk gene with a transportation distance gene, or I'm not quite sure how you're doing that.
What we try to do is to like mix different kind of solutions, but what is a solution? It's a chromosome.
Okay.
It includes all kind of stations, and we try to do it on like an stochastic process to mix it all. So we get another solution that is a new generation, and if you know something about genetics, the other generation will be better than the last one.
Yep.
That's the idea of genetic algorithm. So we just took it if it's the best solution than the last one, than the last generation. But if it is not the best, any other good solution, we just mix it again to find another best solution, minimizing risk all the time, or distance. You can use it for distance or precipitation utility truck if you wanna like to feel it at all and check it if you're gonna find the best solution.
Is the technique being used in the real world at all with any rail companies or trucking companies yet?
Actually, we use this project for Chevron, Texaco.
Okay.
Like all kind of stations, we just like found all kind of positions, like global positions at Bogota to see how they work. But genetic algorithm is also used for different kind of problems like facility location at chemical engineering plants. So it's really useful and it's really flexible. It's not an exact method that you are like tied with a number of variables, but you can use it here a large number of variables, and it can be like more real.
No, we haven't had any.
Any last words for us?
I think there may have been
I think I'm done.
Okay, well, thank you very much.
It's a pleasure to meet you.